What I'd like to talk about today is an interesting document that in mission operations we produced first in 1972 and then a couple years ago in 2004-2005 time frame. Give a little background on it. It's the Human Space Systems Operational Design Criteria Manual, originally published at the end of the Apollo program. And so what they did was gather together the operators who had lived through the design evolution. Most of the people who worked Apollo, many of them worked Gemini, and quite a few of them had worked Mercury. And so they had seen the evolution of how the vehicles operate. And the notion was, well, you know, when we build our next vehicle, and at this time we were contemplating the space shuttle, the idea was, well, let's write down all the things we learned about how not to design a vehicle for purposes of operations, and try to be as specific as we can. When you gather subject matter experts together, that, well, you get a lot of different things. Some of them actually conflict with each other. And so it was, well, let's not do that. Let's call it a criteria document where we will use it as our yardstick to judge new systems that are built, new designs that evolve. And so over, I think it was a period of about a year, with some editors and stuff, the finest minds of how you operate human spacecraft in space wrote down, starting with things they didn't like about vehicles, and tried to become particularly specific about it. And it was organized by the disciplines that we operated in at the time. And so they produced this book called the long-winded title, but culturally we know it as John Common Sense. It's kind of cute in the front of the book. There's a signature page that has Gene Kranz as he was the division chief at the time as a signatory, but it's also signed by John Common Sense to kind of represent, well, this is the common sense wisdom of the operators. The interesting thing is to go back and read that edition of the book. You will find things, or those that understand the way the shuttle works, was that a tremendous number of those lessons learned crept their way into the shuttle program. And in fact, it's an interesting activity. I've read a few of the Apollo experience reports and I think the explicit lesson learned documents, and you'll find many, many synergies, because if you're there on third shift desperately trying to solve a problem of how we're going to tease this spacecraft into doing what it is, you remember that and you say, well, we're never going to build a spacecraft like this again. And that was kind of the emotional tone that led to the building of the book. I have the sense, again, I was just a kid when this was going on, was that there was a very rich soup of visions about how we ought to operate, how we ought to design systems for the future. So the book was obviously, whether the book itself or just the stuff in people's minds, was heavily influential on the operator voice in the design of the space shuttle. I came into a leadership position when we were starting up for International Space Station, at the time Space Station Freedom, and so we had a large number of less experienced engineers. Most of the Apollo veterans had moved on to management or retired, and so we had a large number of people who, we had a few old heads that remembered that stuff, but mostly it was a few folks that Shuttle could spare at the time, and a whole bunch of people we hired from outside. And so we revived the book and had a little colloquia on it and said, well, you go read your section before you go to that preliminary design review. Three years ago, Jeff Hanley, who now the Constellation Program Manager, was head of the Flight Director Office. He said, we need to update this thing. We need to update this thing. And of course, in mission operations, when flight directors get excited about something, everybody follows. And so we spent about a year, Jeff and I, trading off chairing the reviews, where we had people say, okay, go study what the Apollo guys said, see if you understand it, and then either amplify it, talking about the more modern technologies, and I use avionics as an example, there are others, and take the things that we learned during Space Shuttle and Space Station and add to that. So there are sections that had half a dozen short things in Apollo that now run on to 15 pages, and of course it often starts with, well, this thing is a horrible mess to deal with and it takes huge amounts of work. We tried to get it to distill into a positive statement about how the thing should be designed, and it's no accident that some of the richest additions we had there had to do with how you establish and manage command and control and design displays and things like that, things that were not quite as flexible during the Apollo period. And so we managed to get it to a state. We'd all like to do some more work on it, but a lessons learned sweep is always an enthusiastic thing when you start, and then, well, did we get the last bit of updates? Yeah, okay, let's sign it off and move on to something else. The main reason, the primary reason we undertook the update was to force ourselves to drag through the lessons that came out of the Apollo program, because the Apollo systems and mission operations were very different from the Shuttle. The Shuttle was a revolutionary launch and space system architecture, where what we're going to do for Constellation goes back to axially symmetrical rockets with tiny capsules on the top. And so that was the reason we thought we needed to go dig through this and see what we did. And our goal was not to make everything look like what it would mean for Shuttle, but to add to it. And we did struggle a bit with language, where you had kind of an obsolete language. I think we hit a middle ground of making sure that it was interpretable. One of the things we would have liked to have done, but we just ran out of steam, like the scenario I just told about the crew egress in a minute relating to the Apollo fire, was to try to write a rationale, because you can pithily state a design criteria as well as you can state a requirement, but perhaps 8 years from now, when we're, or some number of years from now, when we're doing assessing the preliminary design of the lander, and years beyond that when we go to Mars, that it's important that the stuff be readable and not, oh, what a quaint thing, look what they were using. They used relays back then, oh my God, you know, which distracts from the message. It was quite an interesting thing, and during those reviews, we would come across a lesson learned, and the current specialists who we had look at it say, well, that's interesting, I'm not sure I understand why. And I remember one afternoon we were sitting there puzzling over it. It says the crew shall be able to egress the vehicle within 1 minute. And we say, well, gosh, you can't even get out of the shuttle in less than 1 minute, and all of that. And somebody in the room said, Apollo 1 fire. And of course, this was still very fresh in everybody's memory. And so, well, maybe you can't build spacecraft that way, but you should try very, very hard to make it very easy for the crew to get out of the vehicle. And in fact, that particular lesson learned was a factor in one of the Constellation discussion about requirements on hatches at the Constellation SRR, I think it was. And there was a critical mass of folks in the room. I'm really proud of it. We had a goal of trying to put it on as some kind of feature of design contracts. We've not been successful with that, but as a hip pocket thing that now is accessible through the web as a Word document. It's a tool for our folks, and in fact, having gone through that exercise of trying to understand what the forebears were telling us from their lessons learned and try to couch it in our own language. We carry this as a reference, and every so often we think about, is there some way we could fit it into the program process, but today it's a reference. The mission operations team divides its efforts pretty much among the spacecraft projects, the level 2 system integration activity, and then our own definition of how we're going to fly and what facilities we're going to build. So this helps us with a couple of those missions. What was interesting was the avionics parts of it, because the Apollo experience was very tiny, wonderfully specialized computers, and the use of avionics as a control element of the vehicle was fundamentally a guidance navigation capability. And so our forebears were not able to hand us a lot of lessons that helped deal with the space station design, which is a multi-tier firmware controller computer architecture. And I tend to think that if we had all thought better or thought smarter about what it meant to have 60 computers all talking to each other over varying grades of networks, we might have designed it a little bit different. But interestingly, Apollo didn't help us with those architectural things. This had sat kind of in the back of several of our minds through station. As operators, we have a tenuous relationship with the station. It's the most complex and flexible vehicle we've ever operated, which is bad in that it's complex and flexible, and flexibility means you have to make choices. On the other hand, we have a lot of people that have gotten their hands dirty with how you operate such a complex, subtle vehicle that you have 5 different ways of doing things, and each way is more appropriate, is appropriate to a certain circumstance. Multiple power sources is one of the ways you achieve the availability, reliability, redundancy, that you can lose a power source. And so ideally, you don't want to have to wake up and say, oh crap, what am I going to do because my thing lost its power. You'd like it to be automatically switched over. One of the ancient wonderful technologies of DC systems is diodes, plus and minus problems, but in Apollo 13, when we lost a tremendous amount of power generation, virtually all of our power generation capability, there was, no one had ever expected we would be quite in that box. And so basically you were having to make individual management decisions about what to turn off when and when to bring it back on. The Shuttle didn't exactly implement that, but did a very rigorous and rich. Critical loads have multiple power sources that automatically do that, and the fuel cells have a certain capacity for expanding and contracting the power that they produce. Space station has a very rich system about this, that if you lose, it automatically reconfigures so that if a critical load loses power, it automatically, the other one hops up. But if you don't have enough juice in the batteries, it automatically initiates a load shed, an automatic power down, which in Shuttle is a fairly manual process, exhaustively maintained. Now, lovely outcome of that was, oh, well, you have these wonderful tables that tell you what to power down. Well, if the whole vehicle is there and it's all healthy, it's easy to build those. If you have a thing that's broken and a thing that you no longer trust, but it's good enough if you have to, that will change your priorities. And so we move from control to command. With these things, we essentially set policy that says if you run out of power on this week, you turn that thing off rather than this other thing off first, which means you move to analysis rather than analysis and control, because the control is executed automatically.